Okay, I think that's long enough. Might get into it. You're all good to go, Nick?
Yeah, all good. Thanks,
Cool.
Jeremy.
All right, I'll run through it. A few more people are coming in. So welcome everyone to the final Module A webinar of the year. So we're very lucky to have Nick come back and run through part 2 of points. Just a reminder. Oh, well, firstly, my name's Jeremy Good. I'm the incoming education coordinator for the IRSE Australasia younger members section. So I'll be generally running these or organising these sessions for next year. Just as a bit of a shout, if anyone does have any ideas for topics, feel free to get in touch. It'd be great to hear some feedback or ideas. Just a reminder, I'm sure everyone knows who are sitting it, but the Module A exams, well, all IRSE exams are being sat, I believe, this Saturday. And without further ado, I'll introduce Nick. He did get a bit of a spiel last week, but for anyone who wasn't here, I'll go through it again. So welcoming Nick Coomer. Nick is a multifaceted project manager in structures, rail track signalling and OHWS. He has worked as a consultant in mining, rail and government projects since 2015 in both design and construction, and has a strong passion for developing himself and, more importantly, the next generation of rail and signalling engineers. Nick is currently undertaking the nationally accredited graduate diploma in railway signalling. And I think I'll hand over to you, Nick. It's all yours.
Thanks, Jeremy. Appreciate that. Hi, guys. For those who haven't met me, yes, mechanical background started off with, then fell into track and civil, much to my mentor's disgust, and then found out about signalling in design, construct, sigs and comms in WA, and been fascinated with it ever since. That's why I'm hoping to pass on whatever I can in terms of points. But like I mentioned in the last webinar, reach out if you have questions, if you have suggestions, if you have input as well. I'm not the expert, but I am using the experts around me to present this to you. So from the points, part 1, we looked at some of the terminology for points, the fact that it's points versus switch versus turnout, the same thing, just use interchangeably. Doesn't matter about network. We spoke about the signal principles. We had the fact that we have to move from the normal to the reverse or vice versa. We then have to make sure the points are detected in that position. And number 3, we then have to make sure it's locked in place as we're traveling past it. And once the train's passed, then you can release that locking. And we spoke briefly on some operational hazards that you'd see in points. In part 2, we'll just describe a few more about points motors, some examples around the country, and some common failure modes. And there's some questions from part 1 that I'm hoping we'll get time to tackle this afternoon. Right, so it's Francis Howe. He is the one titled with the Back to Basics Points Part 1 and Points Part 2 papers. The documents I've found online, I've also attached it to the end of this presentation. So by all means, have a read through. It goes a bit more in depth and some good reading in there. And Trevor Bradby and Alexander as well, who helped write that. Now, for those who weren't in the first one, I think this is probably a good time to have a visual video from Network Rail regarding switches and crossings, just the introduction. So just have a look through this. It's a nice intro.
Switches and crossings play an essential role in connecting the rail network. We use them to guide trains from one track to another and to enable lines to cross paths. Put simply, they're the junctions that allow us to create a multi-lined, multi-routed rail network. Or flange doesn't normally touch the rail. Flanges are only a last resort to prevent the wheels becoming derailed. A switch can guide a wheel in one of two directions. A crossing creates a gap in the rail for the flange to pass through. This is a switch. Also known as a point, it's the moving part of the switch and crossing layout, and is made up of two long blades which can move across to guide the train one way or another. This is the switch rail, and this is called the toe. This is called the stock rail. It's a non-moving part of the switch. The two switch blades are fixed to each other by a stretcher bar to ensure that when one is against its stock rail, the other is fully clear and will provide room for the wheel flange to pass through cleanly. This is a crossing. It's the non-moving part of the switch and crossing layout that allows a train to pass in either direction once the switch has been set. This is the nose of the crossing. Either side of the crossing area, wing and check rails are provided to assist the guidance of the wheel sets through the crossing. Crossings can be either fabricated, made up of two machined rails joined together, or they can be cast as a single unit. Modern crossings are now cast from manganese steel, which is an advanced alloy that gets harder with use. This is an important property, as the nose of the crossing can take high impact loads as train wheels pass through.
The most simple form of S&C is the turnout. This is a left-hand turnout. As you can see, it diverges from the main route in a leftward direction. This is how it works. In normal mode, the left-hand wheel rolls along the switch rail, and there's flangeway clearance for the right wheel to continue along the stock rail. The inside surface of the right flange is kept on course by the check rail. This restrains the wheel set and ensures it is directed along the correct route. Meanwhile, the left wheel transfers contact between the different parts of the crossing. That's where there's a high impact load. In the reverse, the right wheel rolls over the switch rail and follows its geometry. The inside surface of the left flange is guided by the check, forcing it to follow the stock rail on the new route. And the right-hand wheel makes a crossing, again impacting a load on the crossing nose.
There are many different types of switch and crossing on the network. They include turnouts, diamonds, crossovers, and slip diamonds. The type we use is determined by a number of factors, including the number of lines involved, frequency of use, and running line speed. Trains travelling at high speeds need long switches and crossings. At low speeds, such as in stations, trains can make tighter turns. Train movements across the network are set and controlled by signallers, who use switches to set routes for trains. Switches can be propelled by various devices. One of the simplest forms is a ground frame setup, a series of rods and cams attached to levers in signal boxes. These are now largely being replaced by remotely operated hydraulic and electromechanical devices.
Seen by rail sides all across the country. This is an HW2000 points machine. This is electromechanical. What we have here is your drive motor. To check the motor has done its job, over here we have an interlocking and detection system. Detection tells us when the points have completed their travel and locked. Locking holds the points in this state, so they cannot be physically moved, so when a train runs over the top, it remains in position. Facing point locks are one of the most important safety features on the S&C layout. They ensure that the points cannot be moved when set. This is important because failure to lock the switches could cause a derailment.
As engineers, we face an ongoing challenge to maintain and improve our switch and crossing assets. Trains can create large impact and lateral forces as they change course, and these forces can cause wear and deformation. Switches and crossings therefore have a limited lifespan before we need to replace them.
Now, you could see in the last area there where there was a bit of motion in the crossing area there. I'll just play from that location.
Trains can create large impact and lateral forces as they change course, and these forces can cause wear and deformation.
It's quite impressive just how much wear and tear that those points and crossings take. The blade themselves at the front, which I'll use a pointer in a second, the blade at the front, and also the crossing area, which we described last week as the frog or the crossing or the V crossing. There's a few different names for it. Now, they mentioned that the V crossing is a fixed point. Later on in this, we'll describe a crossing that isn't always fixed, the nose in particular. Now, the major components, as you saw in the video, the points motor with the detection circuits inside. The contacts they were making a left and a right bridging between the positive and negative, which then told train control whether it's in the normal reverse or the reverse. So in this instance, you can see the switchblade, these little tips here, are closest to the stock rail on the left, which is the sleeper showing on the N side, the normal side. So you can say this turnout or this switch is on the normal lie or set for the normal. Finally, the one on the right-hand side there, if this blade was to move to the right, that would be the reverse side. As mentioned, the spreadsheet or spreader bars maintaining gauge and making sure there's movement evenly across and allows flangeway clearance. Say, for example, on the right-hand side, the chair plates is what this section between the blade, the tip, or the toe, and the heel, the switch heel. That's the part that does actually move left and right. And that slides on these chair plates. And chair plates are generally carbon Rocol based lubricants that allow that movement and does get maintained quite regularly. Now, one of the items that I mentioned already is the toe and the heel. So imagine a foot terminology is used here. There's the switch blades, which could be called a points blade as well. But then I've called a points motor or instead of a switch motor, which is also another term for it. So bear with me, there's probably a mix of terminology, but ultimately they all mean the same thing, and that's rail for you. Now, we spoke about the signaling functions last time. One, points motor does the bulk of the work, which is moving the points from the N to the R and reverse. Then we've got the detection, making sure the position is in the correct normal or reverse lie. And finally, some sort of locking mechanism, whether it's inside the actual points box or actual mechanical lock, clamp lock in the middle of the track to lock it in place until the train has come all the way through. Now, in some cases, because of the large size of these turnouts or switches or points, they actually need multiple points motors. So in this instance here, there is 8 motors moving this blade. It's quite long, it's more high speed, and they also want it to be evenly moved from left to right and at least have some redundancy just in case one doesn't work. Now, what other thing you might notice is that there's an additional motor. So if you can see on this top right here of that image, I know it's very hard to see, that is another motor. Now that is for the moving crossing point, as I referred to earlier. Here's one by VAE. So VAE and Vossloh are the two of the major turnout manufacturers. They supply this from factory. Now that V there is able to be moved left and right, just like the points blade. If you look on the picture on the bottom right, you can see an N and an R, very small, I'm sorry, but if you can make it out, that's usually coincides with the points N and R. So if the points blade is for normal, you can imagine the blade at the crossing is also at the normal. So this is called a swing nose frog, a swing nose crossing, a swing V. There's probably other names there for it, but effectively means it can move to allow that flangeway gap to be cut off and provides a continuous path for the wheels from the points blade all the way to the end on the trailing side. Excuse me. Now, one thing to consider is now we've introduced an extra blade, extra points motor. Therefore, we now need to look at detection of the points as well as the crossing itself. You saw some of the crossing types here. So in this instance, we've got a fixed crossing, right? So you can cross along there and along there, and then this is the opposite direction there. So that's the point, and you can see the shape makes a bit of a diamond, so call that a diamond crossing. Now this is similar in the sense that I'm able to move along this page up to the top of the page, say for example, and I'll follow that line down there if I can move with my mouse clearly. And then finally, at this point, there's a points motor there, or a motor, and that will be driving this crossing blade and that crossing blade to be able to interact and allow traffic to the left of this page here. Now this one here is a double slip, and so that allows a bit of multiple movements for this one to the left, to straight, and then for this one through the straight and then to the right. So there's a few little movements there, multiple motors all around, and you can imagine just how complicated that could be. Now consider another failure point. So we've mentioned you now have to additionally detect the crossing, the swing nose crossing as well. What if you have to move points manually, or power fails and you have to cut power and move it manually yourself? There are power apertures you can cut off and then control the motor by hand. So taking the motor into hand. So is there operational need for it? In the PTA, this is an example of one of the motors. So the left yellow area there is the voltage cutoff aperture. So you insert a key into this slot there, unlock, move that glass guide out of the way, insert the key, turn it clockwise. That cuts off the voltage, cuts off the power to the motor. Then you can insert a larger crank handle key into this. You've obviously got to unlock this lock. It's rather than a key, it's a handle. Excuse me. The handle then you can wind either clockwise or anti-clockwise, and that'll set the points blade to the normal, also to the reverse. So this is one example. There's multiple different types. So it's going to be impossible to go through it all. But generally, you'll hear a bit of a click when it clicks into the normal or reverse point, and then vice versa. Then you can contact train control and ask them, can you detect it in this new position I've put it into? And they'll be able to detect it. So although power is not available to the motor, they'll be able to tell at least detection. In some cases, there's manual levers provided to throw the points from normal to reverse. So in this instance here, you've got a key. You put your foot down, move that lever out of the way, and this tiny little handle, little bar there, gets thrown over to the other side, which means you've now got the turnout in hand. And then you move this lever back and forth as you need to move the points normal or reversed. Right. So then we have areas where we actually want to derail a train. Now, we've been speaking about the need for safety to avoid derailments. So it probably seems strange. I'm trying to say, okay, sometimes we need to derail a train. There might be some operational need for it, or it might be a way to protect the rest of the infrastructure. So these are called trap and catch points. Again, driven by points motors. In this instance, the train can be diverted to the right-hand side toward this barricading here in order to avoid collision head-on with this opposing train. You can see in the far end there. So that allows at least protection of this asset, protection of the people, protection of any sort of assets around this train if there was a head-on collision, and you sacrifice a tiny bit of infrastructure, probably damage, maybe the ground, maybe this pole here, but all in all, would potentially save lives. In a similar vein, this yellow section, that's from the PTA control system there, they have a points motor which controls this particular one, which opens up a gap. Instead of allowing traffic straight through, so from that far end down, if you follow it down, it'll then go, okay, the only access I've got is my diverting little piece of rail, so therefore I'm going to diverge onto the left or onto my right if I was coming down the page. So they typically provided at exits of sidings and passing loops, or where a track joins a main line. Another example where there's a siding that's placed between the two main lines, so up and down main lines there, for example, and there's insufficient room for a single blade catch point. So they want to have a double gauge with two motors, which allows derailment in the center, derails the train in the center of these two tracks, or these main lines. The second signaling function we spoke about, points detection. Now I'm going to go through this very quickly. There's not too much in there. We went through this last week. Electrical contacts are inside the points machine rather than a separate unit. In some cases, there's an external unit that detects, that provides that contact for detection in the normal or reverse. And from the video you just saw a bit earlier, if I could just bring a pointer. As we mentioned, the motor there's some reducing gears, and there's probably a clutch in there as well. Excuse me. The two on the left-hand side are for detection, and those are the little contacts that you can see in the where the mouse is. And then the right-hand side is your locking. So locking, as we said, is something we do in order to make sure the train is safe, so the back end of the train doesn't suddenly get derailed by a point suddenly start moving. Here's an example of a mechanical clamp lock that gives you an idea of just what it looks like. So I'll throw over. In some cases, the notch is on both ends. You'll see this locking bar fit into the center. So that's just one example. Now we've mentioned also in the video that there was locking inside this particular points motor cover. So that generally it is the points bar engages a pin or something that locks that bar into place. And then once power gets removed from the points motor, which means there's no way to move that bar, so it's locked into place. And then once you power back on, you can then remove that lock, bar can move, and then go into the opposite lie. Now, I haven't been able to find a video, unfortunately, of the internals just to have a look at it, but usually it's underneath the contacts, the detection points. So it's and so many different types of models. It's hard to research something like that. So I'll endeavor to find one, but if not, might be a case of reaching out to your points or signal maintenance techs and see if you can get a site visit one day to have a look. Now, in some cases, you may actually want the trains to come through and not be able to fully lock that points in place, and that's only in the trailing side. So the two that goes and merges into one, that's the trailing side. So remember from last week, if I'm facing the points at the blade end, that's my facing. If I'm looking for the opposite end, I'm trailing on the trailing side. So these are called trailable versus non-trailable. So the trailable switches. Now these are generally found in places where you want that operational need. Trams is one example as well, where you allows the points to move out of the way and then revert back to the original position. So let's have a look at this this video from Yarra Trams in Melbourne, just for interest. So the first tram is moving to the right, and this tram that you're in your video of is going to attempt to move to the left. So it's just come to a park. You'll see the points have already moved for the correct location, for the correct line that he wants to, which is to the left. Just notice the points moving just then as you get into the stop.
The free tram zone ends in 2 stops. If you're travelling beyond the free tram zone, touch on your bike.
So how do the drivers determine where they're going left and right? In the trams, it's a bit of a unique environment. There's a transponder underneath, and they press these buttons as they travel over the transponder. Those are the buttons that they see inside the cab. So that's referring to the transponder. And yes, correct, Sam, I'm just reading the chat. That is what the air trams are, the spring-loaded points. So I'll show them in a second. That's underneath the tram. And in between the tracks, there's a small section that's cut out, and that's where the radio signal interacts with a signal box on the underside, which is a transponder. And that gives instructions to the electrical system to switch from normal to reverse or vice versa. So that's their cutout. You can see, you'll start noticing it for those in Melbourne. Now notice these points as the tram comes to a stop. That's when it'll start changing prior to it moving on. So it's currently set against it. And there it moves. Right. So one thing I wanted to mention is that, okay, this also is a trailable, so spring-loaded, as Sam mentioned. So this is the example. So you'll see just a close-up. So if I go back to the video and show you this part where it comes around a corner, and you could see a zoom-in version of this, where you'd think if you were coming from the right-hand side of the page up, there should be a space for your flangeway. So your wheels to be able to interact and go through that path. At the moment, it's set against it. This is, mind you, we're coming from the back end or the trailing end of this of these points. Now, we'd think if this was against the left-hand side, that's the points blade there, then that would allow traffic from this end. So the unique nature of the trams points, they're spring-loaded, as Sam mentioned. The idea is that it springs back after the traffic has passed through. So listen for the clickety-clackety noise that the trams make, and that is the points changing and then reverting back. So this is it. So let's ignore that part. It's coming through this crossing around the bend, and then there's a very light second-hand one. So if I'll just play that again. There it is again. So that's the IRSE trams in Melbourne. Another one is more on the countryside, so the trail walk operation, where switches are locked by these claw locks when a train approaches from the trailing side. So remember we mentioned this is the facing side, where at the moment we're facing it. Now trailing side is the one that's coming back towards us. So from this road and then from that road there. If you follow this one on the right-hand side, you can see there's gaps. I'm able to go across this crossing and then come to the points blades without any of an issue. If I look at this wheel, same again. I don't seem to have an issue. Now, if I'm coming from this road, I can see these points are set against me, that I'm going to have to come into this gap, move this out of the way, and then keep on going towards me, taking the photo. So that's a claw lock. And once the train has come through, the claw lock, the switches return to the original setting and they're relocked by the claw locks. So I don't have a picture of the claw locks, unfortunately, but you might be able to Google something along that. And by all means, guys, jump into the chats and the Q&As. I'm more than happy to jump in and out of conversation. Now, common failure modes. Excuse me. So we've got the points machine, the external factors, the human factors. There might be some weather as well. Let's look at the first one, which is points, the actual machine itself, the motor. So some of the general mechanical issues that you might see are clutch or motor failure. You've got greasing, you're not maintaining correctly, the motor seizes. If you've got moisture and dust in there, there might be some rusting or sand, which leaves a bit of corrosion. That is a possible common failure. So maintenance is generally carried out at regular intervals. Generally speaking, once you open up the points motor, it's quite clean. So in my experience anyway. The electrical power sometimes could be disconnected. There's large cables. Insulation can be ripped about. They might be defective. They might start shorting. Conductors melting. Excuse me. Another one might be a voltage drop. So these machines can have a peak current requirement of say up to 12, 10 to 12 amps when the points begin to move, and then upon completion of the movement. So they are, if they're powered from the interlocking, the higher current requirement just means to avoid any voltage drops, major voltage drops, the cables have to be short. So you need to have power supply close to these points. So voltage drop is a potential reason for electrical power issues. Sometimes the power is derived from traction lines. And so if it's from traction lines, as soon as the train's in the traction area, because of the return path from the overhead lines to the traction return, there might be a bit of fluctuation in voltage at that location. And so if you have already a bit of voltage drop plus the bit of fluctuation, you might not make the cut and get power for your points. There's also the opposite, which is the induction of the points motor. So it might start moving because there's AC power coming through, but the AC motor suddenly gets energized by traction. We've got the external now. So common failure modes for the external area, which is the points, the actual physical components, the blade, etc. As we mentioned before, that crossing and that points blade gets hammered with wheels. So you saw just how much it dipped and how much of a wear. And they generally try and build that crossing nose up after a bit of time, because that crossing gets damaged in such a way where it starts chipping away. All right, so if it chips away, they start building it back up with welding and then reprofile it to make it last a tiny bit longer until they get to a point where they suddenly have to replace the entire crossing, the points blade section, or the entire turnout. So that could be also from the rolling stock. They might have some really bad wheels on the rolling stock, which is leading to some extra damage onto the rail surface. Loose hill blocks, if they've got bolts and whatnot, they haven't been torqued correctly. There's spring washers that they used, excuse me, they're poor maintenance. So generally speaking, at the front end of the installation, but they could also be detected at maintenance intervals as well. If you see a loose bolt, obviously report it. It's going to get fixed sooner or later. Switch rail not connecting with the stock rail. So I mentioned the switch blade is getting little chips taken off. The little chips can then lead to obstructions. They could actually be obstructions and stops the blades from being detected because they're not getting close enough. I don't know if you recall in the first points seminar, so the webinar, the 5 mil gap is all that's needed to provide detection between the blade and the stock rail and the bolt that inside there. So detection could be an issue there. Some human error. So this is generally, typically speaking, to do with installation time. So if you don't get the rodding correct, the stretcher bars or spreader bars correct, the lock rods and the detection rods, you move it from one side, you check the motion, then you move it to the other side and check the detection, check the motion, check the rodding has locked into place. That all comes as part of construction. There's checklists and whatnot to ensure that this doesn't become a problem in future. And there's also maintenance gauge checks along the way and check the motion at regular intervals after installation. So there's multiple attempts at making sure that these points are maintained and looked after and there's nothing going wrong from the usual. Finally, some weather impacts. So although it's not as big a deal for snow in our country at the moment in Australia, but there are instances where hail or snow, and if it's still cold outside, that it would still get lodged in between the blade and the stock rail, excuse me, leading to obstruction. And obstruction means no detection. So that's one possible failure mode. Another one is actually the humidity. In some areas of the country, humidity is a big issue. Humidity and electrical components don't go hand in hand. So if there's rust, if there's corrosion, if there's shorting, that could be an issue. If there's lack of dust and seals around the points motor covers, that also makes sense, right? So need to account for all that, or at least be maintained in such a way that you detect these before they become a problem. Now, cold, frost, and heat. Heat is also a thing. So thermal stress, a steel expands in heat, contracts with cooler temperatures. There's a allowance at the end of the heel blocks where there's a bit of a stop. I won't go too much into detail, but if you look at any manuals from VAE or Vossloh, they'll be able to tell you how to adjust these blocks to allow a bit of growth and a bit of shrinking, but within a certain tolerance. So it doesn't allow you to fully, stretch out all the way and then provide a blade that's sticking out. And it doesn't allow you to shrink too much, which means that then you have detection issues. So there's a block that allows for that stress element there for steel. And I've put in other in there, but I'm just wondering if I can put it to the group. If you have any other failure modes and whatnot. Otherwise, there's some questions from the part one that I'd like to go through. But in the meantime, by all means, use the chat and put your comments in, your questions or anything else. So while we're going through that, one of the questions was failure modes in this presentation. We've already covered most of that. If there's any more that people have noticed in their walk of life, by all means, jump in, let me know. One of the questions was a clearance point marker from part one. So in the meantime, guys, add your questions as you see. So clearance point markers is from the ARTC. They have an area where they go, okay, well, this is the clearance point markers just outside where the crossing is. So this is the junction where it splits into two. That's the points motor. Now they nominate that point where rail traffic is deemed clear of others. So that traffic on this loop line and then this main line is clear of each other. So therefore, if a train's parked up here, it's not going to interact with any trains moving along this line. Yeah, so that's their clearance point. Clearance point markers, not always used, but identifies the clearance point. And then in ARTC again, in their standards says it's not always used, but it may be used. So if you've got it in your network, by all means, shout it out. but typically it's related to this rolling stock outline that ARTC have. Each network has their rolling stock outline that determines the kinematic or the rolling stock profile that he can be sitting inside. Okay, now if you had the maximum size of your converging traffic from one end and one side and the other side, you overlap each other. If they are interacting, obviously that's going to be fouling. Once it's cleared and they're not going to be interacting with each other, that's the point where you put your clearance point. And one that I like to add is courtesy of Mr. Brendan Leese. He's helped me out with this. There was a question about how points are dealt with in the CBTC area. So I've got some notes from him, so bear with me. I'm not a CBTC expert in any means. And if there's other guys who want to jump in, guys, girls, please jump in. But effectively, what he told me is that the hardware is effectively the same as any CBI conventional or relay works object controller there, gives the commands, also returns that detection status there. The interlocking is also similar in the sense that it's locking, release the locking, approach locking, release the locking, and points movements requests. Now the moving block system that they have implemented in the metro tunnels in Melbourne, which is CBTC, that is a bit different. So in the sense that you can actually release the points earlier because you've got a small area for it to work rather than a fixed block. So points track will also have a conflicting point at the front where it'll tell you, it goes back to the CBTC movement authority and just goes, okay, are points detected? All right. Is it also detected in the correct way that I'm supposed to go for this T1 train? And then the train protection system then determines, okay, well, it's not going to exceed its authority. It's going to stop it at that conflict point prior to that points. So in the system at Metro, they use the M23A points machines and Ebiloc OCS 950 object controller alongside. So there, the core signaling principles remain unchanged. Effectively, you set and detect and lock points in front of the approaching train prior to issuing a movement authority. Then you retain that locking, making sure it's set. Then you prevent the points from moving. So again, the three signaling principles. And then also added flank protection from any opposing routes there. So that, that gives an answer to that question from points part 1. So that was very interesting for me to learn as well. Any questions in the chat system there? So one of the questions is saying, Sam, based on my experience, causes for point detection mechanisms not picking up. It could simply be as simple as the contact between the surfaces. There's usually a little nub or stub in the stock rail on the web that might not be aligned. The main issues were actually related to the physical installation and tamping of it. If there was some sort of misalignment in the rail where the sleeper was slightly off or skewed, or because the sleepers were slightly skewed, so that means the gauge was slightly different at the front, that provided just enough of a gap between the blade and the web of the rail, web of the stock rail, and the blade that's coming in and interacting with it, that it just provided just a tiny bit of a gap, which meant, unfortunately, you're not going to get detection. So that was one of the main issues we had. So having a checklist as part of construction was the reason for that. That's a good question, Sam. And you've got a mention about the typical claw lock mechanism there. I'm happy for you to explain this section here. Looks like that's the part that's clawed. Interesting. Thank you very much for that. That was who's that from? Bars. Thank you. Is there correlation with summertime? Sam goes into us. So in terms of point detection mechanisms not picking up summertime. So yeah, so that one of the failing modes I mentioned was heat, so not just snow. Heat can affect the length of the blade. If the blade is slightly longer than it's not setting inside, so as it moves, there's might be a bit of a groove for it to sit against the stock rail. If that groove is now, it's a bit of a curved groove, so if the points have grown to such an extent where it's not set within that tolerance, if that block at the back of the heel is not stopping that growth to go too far out of place, then yes, then there is a issue with heat, plus the length of the blade is too far, which means there's now a gap between the blade and the stock rail. And that means there's no detection, or at least there's issues with detection, or it might be intermittent. That's a very, very unlikely scenario nowadays with the heel blocks. I forget the name of the spot that reduces that stress and increases. A good question. Any other questions? Comments, questions? We've got one for Joe. Sorry, Joe, I just saw your comment at the very start. Moving crossing is normally known as SNF, spring-nose frog, which can be as per VAE, 2 blades which slide as they move from N to R or R to N. There's also what is a pivot blade, similar to the hand of a watch. We can divert a train from N to R, R to N. There you go. I'm not familiar with a pivot blade terminology. That's good.
Just having a look near Q&A. I don't think we have anything there.
It's mostly in the meeting chat, which is good.
Yep.
Sorry for last time. Apologies, I didn't look at both the chat and the Q&A, so thank you for keeping it all in the chat. I think it makes it easier to view. But yeah, at the back end, I've got some articles and the link to the part 2. In the part 1, there's a link for the part 1 article in the part 1 webinar. By all means, reach out to myself, Richard, to Jeremy to get access to that. If you're part of the IRSE Australasia group, more than welcome. You'll have access to it. You don't have to be a signal engineer or of any sort to be able to join that committee, by the way. So by all means, more the merrier. Come in. Ooh.
Great, thanks, Nick. Might wrap it up there. Yeah, thanks for running those 2 sessions. That's it's really great. Also, look, if anyone has any other questions post the session or on watching the recording, yeah, feel free to reach out and we'll try and get some info your way. Yeah, great. For anyone doing the exam on the weekend, good luck. And yeah, it's the last webinar for the year for YMS, but we'll catch you next year.
So there's one that's just popped up. Where was the person doing the signal engineer course? I think it's that.
Is that the grad diploma?
Possibly, right, Ryan. Not sure if you want to elaborate on that, but if you're referring to the grad dip or railway signaling, that's a course you can go through Competency Australia and apply for that course. Generally speaking, you need a mentor to help you throughout the course, as well as just a bit of a CV or the description of yourself and why you want to do that and apply for it. So that's on the Competency Australia or IRSE website. It should be able to tell you what that is. And Sam, what's the question here? Maintenance crews are called for point malfunction when they attend no fault found or reported. That's not sure if I can answer that, Sam. Why maintenance crews report no fault found. So yeah, typically if there's any fault or detection or any sort of ride issues with the train drivers, sometimes they might call a point malfunction. Yeah, it's an open-ended question. Unfortunately, I do not have an answer for that one. Yeah, maybe if someone else wants to jump in, more than happy to put you on the mic. But yeah, typically there's a bit of competition between rolling stock and the track and civil maintenance team. So and then also the signaling as well. So maybe yeah, there's a bit of a. All right. Well, thank you guys.
Thanks, Nick. Thanks, Jeremy. And just like to wish everyone all the best for the exam on the weekend for those who are doing that. Thank you, everybody.
All right. Bye-bye.